presented by Caltech.
The theme of this workshop is monsoons, and today we're going to kick off the workshop with 4 lectures that will provide a summary of our current understanding of theories of monsoons, past monsoon climates, both in the deeper past or more recent past, and future projections of monsoons and tropical circulations more in general. So because this lectures today will provide a great background for all the workshop participants, but also for other people who are interested in that Caltech community, I really keep my introduction very, very brief, and I'll just try to say a few words on the goals for this workshop. So as I'm sure William Booth, our first speaker, will describe way more in details than I will be able to here, monsoons are thermally direct circulations that are intimately linked to the seasonal cycle of the overall overturning in the tropics and associated convergence zones. This can be clearly seen by looking at maps of the long-term mean precipitation over the Earth's surface for the July long-term mean, Northern Hemisphere summer, and January, Southern Hemisphere summer, as described by one global precipitation data set, the GPCP 1 degree daily. There is a lot of information that are contained in these very simple maps. One, of course, is that most of the precipitation over the Earth's atmosphere does fall in the tropics, 30 degrees north and south of the equator. It's also interesting to note the differences in the seasonal cycle of tropical precipitation over the oceans and over the land. Over the ocean, precipitation is organized along narrow in latitude and elongated in longitude convergence zones associated with the ITCZ, whose seasonal cycle is quite muted both in terms of intensity and position, especially over the Pacific. The ITCZ remains always north of the equator, even during the Southern Hemisphere summer, and controls on the mean northward position of the oceanic ITCZ and migrations on different timescale is a topic that has generated a lot of research and enthusiasm in the large-scale dynamics community in the past 10 years, and I hope that we'll review some progress that has been done on this topic as part of this workshop. If we look over the continents, we see that there, the seasonal cycle of precipitation is way more extreme, where dry winters are alternated with very wet summers, and where convergence zones can migrate much further poleward away from the equator than what happens over the oceanic region. So it's really this seasonal migrations of the convergence zones in the tropics and subtropics into summertime subtropical continents that we now understand are associated with monsoons in the northern hemisphere, in addition to the Asian monsoon, which is the most well-known and most well-studied of monsoons. We also have the Western Africa and also a smaller North American monsoon, and we have corresponding monsoon systems in the southern hemisphere. So it is obvious that monsoons really are prominent features of the large-scale tropical circulation. They also contribute greatly to the global hydrological cycle. They also have strong societal impacts in that they support the water supply of densely populated regions and rapidly growing economies. But despite their importance, there are still many questions that remain outstanding in monsoons. In particular, controls on the spatial and temporal distribution of precipitation in monsoon regions and oceanic tropical regions as well remain debated. Understanding how monsoons will respond to anthropogenic forcing is one of the main priorities, and yet it remains a challenge in climate sciences as future projections remain uncertain. I have myself worked on monsoons in the past. It's a little bit over than a decade now, and I think it has been really a very exciting time to be working on this topic. Recent advances have been made in studying different aspects of the monsoons, from paleoreconstructions, theories, observations, and modeling. So Tim and I really felt that this was the right time to organize a workshop with the scope of connecting recent advances in different communities that have been studying the monsoon. So really, our overarching goal here is to build a more comprehensive understanding of monsoons, bringing together these different communities to study monsoons and understand their responses to perturbation across different time scales. So we have identified 4 goals for the workshop that are summarized here. So the first one, we would like to summarize emerging perspectives of the governing dynamics of monsoons, identify sources of remaining uncertainties, and discuss ways to reduce or better constrain them, reconcile monsoon changes in the instrumental and paleoclimatic records with expectation for future changes. For instance, how do different radiative forcing affect the monsoon response, and develop strategies to integrate perspective across disciplines that will address these outstanding challenges and will allow to make progress. Of course, these are just 4 of the goals that Tim and I have identified, but this is not just our workshop, this is all the participant workshops. So I think that you have yourself been thinking about goals that you would like to see added to this list. So keep this in mind as we keep working together on this topic. I also would like here to emphasize the fact that although we are not directly connected with this initiative, the WCRP Grand Challenge on Clouds, Circulation, and Climate Sensitivity has identified the need to better understand what controls the position, strength, and variability of tropical rain belts as a key scientific question to make progress on the global and regional climate problem. As summarized in a paper that has appeared just last month on Nature Geoscience by Boni and co-author in 2015. And as part of this initiative, 4 key questions have been identified around which their suggestion is that the community should work together to really make progress rather than following separate lines of research. And these questions include the role of convection in cloud feedbacks, what controls position and strength of the storm track, the role of self-aggregation in convection, and again, what controls the position, strength, and variability of tropical rain belts. So in this respect, the goals of our workshop are very well aligned with this WCRP Grand Challenge initiative. So I will stop here because we have 4 great lectures ready for us today, and I'll give the floor to our first speaker, who is William Booth, and maybe if you start while I give some brief introduction.
Should be easy.
Should be easy. And you have the mic?
Yes.
Yes, great. So I'll just say a very few words. It's okay to call you Bill?
Yeah, please do.
So Bill Booth is an associate professor in the Department of Geology and Geophysics at Yale University, where he's been since 2010. Before then, Bill got his PhD at MIT, working with Kerry Emanuel, where he finished in 2008. He then moved to Harvard to work in Jimin Kwang's group as a postdoctoral fellow, sponsored by 2 fellowships, and Hughes and a Daly fellowship. And then he moved to Yale in 2010, where he's been since. Bill's research interests are focused on understanding the interaction between precipitation and smaller scale motions and larger scale circulations, with a specific emphasis on monsoons. He has worked on different topics, made a number of important contributions, from working on idealized axisymmetric models of Hadley circulation, understanding and elucidating the role of topography in the Asian monsoon, and more recently working on the role and the dynamics of synoptic disturbances in the Asian monsoon. His work has already been recognized by a number of awards, including the AGU James Holton Award in 2010, an ONR Young Investigator Award, and an NSF Career Award. And today he's gonna give us a review of energetic and dynamic theories of monsoons. Thanks, Bill.
Thank you, Simona, and thank you for having me and all of us here. I'm really looking forward to the interactions that come about this week. I'm going to try to give this as some sort of combination of a primer on monsoons and the energetic, and unfortunately, because I wrote in the abstract for this probably enough content for a 3-hour talk, not a 30-minute talk. I'm really not going to get it much into sort of the momentum budget dynamical controls on monsoons. But I'm going to try to have a talk that's sort of both a primer and has a little bit of something in it for those of you who know a little bit more about monsoon dynamics already. This is an image just to set the stage of the South Asian and African monsoon regions. Happens to be from a satellite image from a time last early September when there were tremendous floods here over the northwest region of India due to an interaction of a synoptic scale cyclone that drifted in from the southern part of the monsoon region, the Bay of Bengal, and an eastward propagating mid-latitude wave on the subtropical jet stream. But the idea is just to show the whole region and the large amount of complexity on different spatial scales that occurs there. Before I begin, I'd like to just briefly acknowledge financial support from the NSF and the Office of Naval Research, together with work that appears in these slides by John Hurley, Ravi Shekhar, and Trude Starelmo, who are all or have been at Yale. Simona mentioned the different monsoon regions, and I drew red boxes here around what I think many would agree are the different monsoon regions in the northern hemisphere during its summer solstice season and the southern hemisphere. And you can see this sort of large-scale migration of the rainy areas from one summer side of the equator to the other summer side of the equator as the seasonal cycle progresses. And globally, a large fraction of rain during the solstice seasons falls in these monsoon regions. And so when we're talking about monsoons, if we include the American, the African, and the South Asian, Australian monsoons, we're really talking about the general circulation of the troposphere during the solstice seasons. We're talking about the Hadley circulation. It's sort of made up of the flow in these different monsoon regions. And it's become traditional to think of monsoons conceptually in a very idealized sense as this meridional overturning with warm air rising in the summer hemisphere over some off-equatorial continent and colder air sinking in the winter hemisphere, cross-equatorial flow that because we are on a rotating planet, you have the trade winds. This is supposed to represent a vector going into the board. These trade winds are reversed in the summer hemisphere to become the low-level monsoon westerlies. And you have a lot of vertical wind shear with strong low-level eastward flow in the summer hemisphere and strong upper-level westward flow that creates vertical wind shear that, say, for example, suppresses tropical cyclogenesis, the formation of strong typhoons in the South Asian region during summer. That sort of 2D view of that thermally direct meridional overturning might seem to fall apart a little bit when you look at a lat-long distribution. You might think, well, monsoons are these very complex three-dimensional circulations, but it does hold up when you take a sort of limited zonal mean average. This is a plot of precipitation in colors and the low-level 850 millibar horizontal wind, and you can see that you have your trade winds here, your westward flow in your winter hemisphere, your cross-equatorial flow. It's concentrated in the western part of this Indian Ocean basin in the Somali jet, and then your low-level monsoon westerlies that are rising in the summer hemisphere to produce precipitation over and near the coastal regions of this off-equatorial continent. So that 2D view does hold up. Now, what I've just told you, though, is largely descriptive. And what I'm going to spend the rest of the talk getting into is the question of how do we understand both the mean state and the variability of monsoons. And I have here a number of examples of just notable things that have happened on different time scales, notable variations in monsoon strength that have happened on different time scales. For instance, there are droughts in South Asia. In 2002, there was a tremendous drought in India with something on the order of 83 or so % of the normal rainfall, which is nearly as low as it gets in the observational record. So there's a lot of interannual variability in monsoons. There's decadal variability. Probably many of you are familiar with this decades-long Sahel drought that occurred 20 to 30 years ago. There's right now a 30-year drying trend in East Africa, just as the Sahel has been recovering. We worry about the response to anthropogenic forcings, including greenhouse gases and aerosols and changes in land surface use, say due to agriculture. And there are a number of people here who think a lot about the variability of monsoons on much longer time scales, the response to orbital forcing and to changes in continental configuration and topography. And so how do we think about monsoons and how they will respond to all of these different forcings on all of these different time scales? And I've listed here what I see as three ways that people commonly think of as monsoons. The first is probably the one that most pervades sort of layperson perspectives on monsoons and is still surprisingly pervasive even in the monsoon dynamics community. People think of surface temperature gradients driving the flow. I'm going to just mark that as just wrong, and I'll show you a piece of evidence for it. But I still think that you'll often hear statements such as land-ocean temperature contrasts are supposed to increase as the Earth warms, and so monsoons should strengthen. And that's something that I think the field has known to not be true for probably well over a decade now, but it's something you still see occasionally. So one of the big points of my talk is to just, for those of you who maybe don't work in this field on a day-to-day basis, to really convince you that this is true and to get you out of thinking of this as a way to think about monsoons. The other idea is this convective quasi-equilibrium framework, theoretical framework, which I will spend a little bit of time thinking about, gets into some details mechanistically, but a little bit, unfortunately, somewhat diagnostically. In other words, it doesn't necessarily allow us to predict what will happen to a monsoon given a forcing, but it allows us to think about it maybe after we know the answer and understand it a little bit better. And then the last one is sort of the vertically integrated atmospheric energy budget, that the energy is conserved, and so we know if we can write down an energy budget and think of our forcing, whether it's a greenhouse gas perturbation or a high latitude sea ice change, that we might be able to, if we can encapsulate the forcing as an energy budget, as an anomalous energy source, we can use the energy budget to figure out what might happen. And this is something that then is prognostic, but unfortunately, because the energy budget doesn't tell us the details of the mechanism, it's not really, doesn't give us so much of a mechanistic response. So these caveats will become a little more clear through the talk, I hope. So I'd like to begin with this just by showing what I think of as a single sort of graphical disproof of that idea, that surface temperature gradients drive the flow. So this is the African region right here. You can see the African coastline in light gray. And what we've done here is we've drawn a box around this western part of the Sahel, and we've averaged rainfall over this box, and then we've regressed the low-level air temperature on precipitation in this box. And what you get out of that is you get this map that shows essentially what the air temperature looks like with anomalously cold temperatures being in blue, anomalously warm in orange, during a enhanced rainy year of the West African monsoon. And you can see that this big cold band on the edge of the Sahara over the Sahel region that indicates that when you have a strong or a wet monsoon year in West Africa, it's colder than normal. And so you can't really think of the land surface being warmer than normal, creating a stronger land-ocean temperature gradient, giving you stronger monsoon flow and more rainfall, right? The observations show that it's exactly the opposite that occurs. And this holds up in other regions. I'm not going to show you that. I'm not going to go region by region through this, but we see that in India, Australia, southern part of Africa, and the Americas also. I'm going to get right into some alternate ways of thinking about monsoons, that if we can't think of them as surface temperature gradients driving the flow, land-ocean temperature contrast driving the flow, how do we think about monsoons? And convective quasi-equilibrium is the moniker for a modern theoretical framework that's often used to think about monsoon dynamics and other large-scale tropically, convectively coupled tropical circulations. And it really posits that moist convection does not act as a heat source for the large-scale flow, that you can't think about the latent heating that occurs in the precipitating cumulus clouds as somehow switching on and then driving these large interhemispheric circulations. But that instead, what moist convection does is it just maintains the vertical profile of temperature in the troposphere near that of a moist adiabat. Just like in a dry convecting atmosphere, you would expect to see temperatures near a dry adiabat, where temperatures fall off at a rate of 9.8 Kelvin per kilometer. And so the idea is that moist convection is a very fast process that keeps free tropospheric temperatures in a near equilibrium state, a quasi-equilibrium state, with anomalies in the energy content of air below the base of clouds. And I've written that here as the moist static energy, the sum of specific heat of dry air at constant pressure times temperature, plus the geopotential height, plus the geopotential energy, plus the latent heat of vaporization times the specific heat, specific humidity. And the idea here, schematically, is that if you have a profile with a certain amount of moist static energy below the base of cumulus clouds and a certain temperature, and these two are in a rough equilibrium state where there's not a lot of convective available potential energy, that if you warm and or moisten the air below the base of cumulus clouds, you'll create energy for convection. You'll get convection. It will heat the free troposphere. So you do have latent heating. It warms the free troposphere. And then you get downdrafts that cool and dry the air below the base of cumulus clouds that then reduce that initial perturbation. And what you end up with is a perturbation relative to your initial state in tropospheric temperature averaged through this convecting layer and the energy, or the moist static energy, of air below the base of cumulus clouds. So these two quantities track together: temperature in the convecting layer and moist static energy below the base of cumulus clouds. And when we put that in the context of this large-scale overturning circulation, we see that we have here, and on the bottom plot, here's the equator, here's the North Pole would be out here, South Pole would be back here. Here's your cross-equatorial monsoon circulation, air rising in your summer hemisphere and precipitating. And we have here drawn at the bottom this plot of the moist static energy, or you could equivalently think of this in terms of equivalent potential temperature, theta E. And you see there's a maximum here off the equator, which is maintained by surface fluxes of sensible and latent heat that are the energy for which is supplied by radiation. And then that convection maintains the free tropospheric temperatures in quasi-equilibrium with this low-level theta E maximum near the rising branch of the circulation. And then you have temperature falling off as you go toward the winter hemisphere or toward the North Pole in the summer hemisphere. And those temperature gradients in the free troposphere are weak, and the troposphere is stable to convection away from this convecting thermal maximum. Now, this is a schematic that, although again this sort of a two-dimensional map view, or three-dimensional if you think of it in terms of looking at lower and upper levels, which are what's represented here. The black contours show the upper level temperature, 200 to 400 millibar average temperature, so upper tropospheric temperature in black, and near surface moist static energy in colors. And so this is giving us sort of a three-dimensional view of the thermodynamic structure of the boreal summer atmosphere. And you can see that the South Asian monsoon is really a global temperature maximum. So these sort of 6 monsoon regions that I outlined earlier are are not roughly equal. The South Asian monsoon is located further poleward and is stronger than any of the other monsoon regions. And you can see that this global temperature maximum lies almost directly over the global maximum in near-surface moist static energy. The actual maxima of just 2 meters above the surface moist static energy are here over the Persian Gulf and Red Sea. But if you go up just a little bit higher, these sort of vanish right here because of the large amount of dry and therefore very low moist static energy air in these regions. And what's left is this moist static energy maximum over the northern part of India, the northern but unelevated part of India. So this sort of convective quasi-equilibrium view, thinking of near-surface air moist static energy, upper-level temperature, sort of being coupled together by moist convection, it holds up, seems to decently describe the mean state. It also seems to decently describe interannual variability. When we do that same exercise that we did before of averaging rainfall over this blue box and then regressing near-surface moist static energy, or here I think what we actually did was near-surface theta E, on that rainfall index, what you see is that you see that the moist static energy is larger over India, a lot larger over India than it is over the ocean next to India. So you get during enhanced rainy years of the South Asian monsoon. So in other words, during strong monsoon years, you get an enhanced land-ocean moist static energy contrast. Now, this is the same plot that I showed you before, but when we compare that to regressions of the rainfall index on temperature or on specific humidity, you can ignore these green lines for now. You can see that India, a lot of continental India, the gray lines right here are coastlines. Here's the Indian subcontinent. You can see that India, during enhanced rainy years, is colder and the air is moister than usual. And so in some sense, you might think that's maybe not a surprise. When it's raining, the land surface usually cools off and the air above it gets moister. But it happens in a non-energetically conservative sense, meaning that the enhanced humidity is more than enough to compensate for the colder air so that overall you get a higher energy content during enhanced rainy years. In other words, just getting back to my earlier point of don't think of South Asian monsoons or monsoons in general being stronger when there's an enhanced land-ocean temperature contrast. In fact, the land-ocean temperature contrast is weaker than usual. There's an enhanced humidity over the land surface, but you really see the enhanced land-ocean thermal contrast when you look at moist static energy. And so that's one way to think about monsoons, this sort of convective quasi-equilibrium framework. And I'm going to now launch into this other framework of using this moist static energy budget, both of which, though, I'm trying to get you to think of in terms of quantities that are energetically conserved, sort of energy going into the land surface from radiation, coming out from the land surface to the boundary layer in the forms of sensible and latent heat, and then thinking what happens either via the sorting of energy vertically by moist convection or by thinking of the whole energy of the column integrated vertically. So the idea behind this vertically integrated energy budget view of monsoons is that you can take this moist static energy variable H and you can look at its north-south flux. So V is your northward wind here. We're multiplying V by the energy content H. We're going to integrate it vertically through the troposphere, through the entire atmosphere here. And then we're going to ask the question of how does that balance for the energy that's supplied to the atmosphere by radiation surface fluxes of sensible and latent heat. So in other words, this equation that I've written down here is just the vertically integrated energy budget for the troposphere, where on the right-hand side we have the energy input to the atmospheric column by surface fluxes of sensible and latent heat, and energy taken, and the sum of those plus energy taken out of the column by radiation, by long-wave cooling to space, essentially. And this energy put into the column by these energy sources of radiation and surface heat fluxes has to be balanced if you want to achieve any sort of steady state by the divergence of energy by the circulation. So this overturning circulation, what it does from an energy point of view is it diverges energy out of the regions where you're inputting energy to the column by surface heat fluxes and radiation. And so this is a profile, a vertical profile of the moist static energy in the atmospheric column. And you can see that it's relatively high near the surface. It decreases to a minimum in the mid-troposphere. And then it increases as you go up toward the tropopause. So you have an atmosphere that would be, if you looked at the energy that didn't account for that stored in the latent heat of water vapor, so if we took it that LVQ term, this would just be a monotonically increasing function, but because the lower troposphere is moist, that LVQ term makes this non-monotonic with height. And if we integrate this vertically, what this amounts to is thinking that you have inflow of energy at somewhat high levels near the surface. You have upward motion sort of through this minimum, and then you have outflow at upper levels where the energy content is actually typically a little bit higher than it is near the surface. And what this means is that because this difference between the low-level energy and the upper-level energy is relatively weak, it means that these moist circulations are less efficient than dry circulations at exporting energy from the column. And it also means that though, because this upper-level energy is a little bit higher than the low-level, that this thermally direct circulation is also energetically direct. It exports energy from the region where it's being input to the atmospheric column by eventually radiation when you go back in the chain of energy transfers. Now, I've just moved this up here on the plot. I've plotted schematically the northward energy transport as it would look schematically during the northern hemisphere solstice season. So here, remember that this is a northward energy transport. So where it's positive, you have energy flowing northward toward the North Pole. Where it's negative, you have energy flowing southward toward the South Pole. And you can see that this zero line right here, where the northward energy transport reaches zero, is your monsoonal manifestation of your intertropical convergence zone, or it's the rising branch of your monsoon circulation. And so south of that rising branch, you have this circulation transporting energy southward, and north of it, you have this weaker summer circulation transporting energy northward. And this energy framework is useful when you think about an energy source being imposed somewhere in the domain. And putting this energy source far from the rising branch of the monsoon is what I've done because it's been, I'll show you in the next few slides sort of the justification for this. There have been thoughts about how high latitude thermal forcings can affect monsoon precipitation. Some people in this room have worked on this a lot more than I have. And so I'm essentially summarizing their work here. But what the idea is that if you put in an energy source here, the energy source has to be balanced if you don't want the energy locally to either blow up toward positive or negative infinity. It has to be balanced by a change in the energy flux divergence in this region. In other words, by the slope of this line has to change. So if we put in an energy source here, this line has to get, the slope here has to get less steep because you need to converge less energy into this region if you're putting in an anomalous positive source. But in the rest of the domain, you didn't change Q. You didn't change the source of energy to the atmospheric column. So the slope of this line can't change in the rest of the domain. Now, in order to meet this boundary condition, it actually has to change a little bit somewhere. So I've sort of put that in after the fact here. But what this means is that note that this zero line, where this energy flux reaches zero, then has shifted, has undergone a north-south shift. And this is my only animation in the talk. So that's all you get as far as fancy movies. But what you see is that what I've drawn here schematically is that this rising branch of the circulation has shifted southward to be consistent with the zero line of the energy flux, or what people often call the energy flux equator. Now, this goes back to some work by John Chang, that's summarized in his review paper in 2012. And I talked a little bit about the motivation for this, which is this observation from paleo proxies that you can see these large shifts and large changes in monsoonal rainfall that occur temporally coincident with large changes in high latitude thermal forcings or temperatures. And what was done here, what John did here in this plot from his review paper, is that he imposed a sort of, just put into a global climate model a cooling, put in a cooling in the North Atlantic, the fairly high latitude North Atlantic Ocean. And then the colors here show the temperature response, the surface temperature anomaly that was produced by this high latitude cooling. And the contours, dashed contours being negative, the gray dashed contours being negative, show the precipitation response. And so you can see that here over the over the whole African region in general, you have, in response to this North Atlantic cooling, this imposed North Atlantic cooling, you have strongly reduced rainfall over the Sahel region. You have your Sahara Desert getting cooler and your Sahel region getting hotter as the rainfall over the Sahel decreases. And so this is an illustration of that sort of energy budget response, and that schematic that I drew in the previous slide is the way that you can use to think of this monsoon region responding to this high latitude thermal forcing, energetic forcing. Now I'm showing you here that a result from work that one of my students, Ravi Shekhar, has done in a beta plane model, so an highly idealized model where we put a continent off the equator in the summer hemisphere. Here's the northern pole is up here, south pole down here, here's the equator. We have a grassland and we have a desert just north of the relatively narrow grassland region. So this is meant to be an idealization of West Africa and the Sahel. And we've subjected this beta plane model to a very wide range of thermal forcings. These lines represent the prescribed sea surface temperature, where we've put in some anomalies near the equator that represent changes in the magnitude of the equatorial cold tongue over Africa, changes in what would be the Mediterranean warm pool region, and large changes in these lines here represent the land surface albedo, or the ocean surface albedo here, where we've changed very dramatically the surface albedo of the desert, of this idealization of the Sahara Desert. And there's a lot of details here, but I'm not going to show you them. I'm just going to show you this one sort of synthetic plot where each row here corresponds to a different thermal forcing. These are sort of Mediterranean warm pool, the Mediterranean getting warmer. This is desert albedo changing. This is the equatorial cold tongue getting colder. You don't need to really be concerned about this, just to know that these are a lot of different imposed thermal forcings. And then what's plotted here is precipitation. And the blue lines roughly outline the heavily precipitating regions. The stars are the intertropical convergence zone, so where the location of the precipitation maximum. And the squares are the energy flux equator, so that line where the northward energy flux goes to 0. And you can see that the energy flux equator actually tracks the intertropical convergence zone. This circle here is a little bit tangential to my talk today. It's the latitude of the Saharan heat low, or the idealized heat low in this model. And although there's a lot of details that I'm not going to be able to talk about today, what you can see is that this idea of the energy flux equator being roughly spatially coincident with the intertropical convergence zone and them shifting poleward together as you look at a broad range of thermal forcings roughly holds, and means that you can, is sort of evidence that you can think of, you can use this energy budget framework to think of the response of monsoon to a very large range of different types of categories of thermal forcings, and it seems to work decently well. Now, one caveat is that although I've mentioned that the energy budget might, in a way that convective quasi-equilibrium was not, because convective QE, you just have this state where low-level moist static energy is in equilibrium with the temperature, but you don't necessarily know how you got there. so it doesn't necessarily allow you to look at it in a prognostic sense. I've argued that the energy budget is a little bit more prognostic because you can think of putting in an energy anomalous source or sink, examining how the circulation has to change to give you a shift in the energy flux equator. But there are large feedbacks, there are large energetic feedbacks. And so what I'm showing here is, again, in this model, just to give you a reference here, the solid line is the energetic forcing that we've put in by a strong increase in the surface albedo of this idealized desert. So we get this roughly 40 watt per meter squared anomalous energy sink over the desert region. And the dashed line is the response of the energy budget to that forcing. And you can see that it's large. It's just the response in the energy budget due to changes in ocean surface evaporation and changes in cloud radiative forcing is just as large in magnitude as the forcing. And there really isn't, at least insofar as we've been able to devise it from this model, a sort of simple, straightforward way to think about the feedbacks. They seem to arise from a variety of physical processes. And so this is a caveat. Now, I want to end by my last few slides are just going to be on some work that I've been doing, looking at shifting gears a little bit to look at abrupt shifts in monsoons. And the reason I've picked this to put in this talk, one is because it's something I've been working on now, but also because I think that it illustrates a situation you can get into if you think of this land-ocean temperature contrast as forcing monsoon circulations. And I've put here, I've maybe done something that's, perhaps some of you will think it's not terribly nice, but I've picked on a number of papers in these prominent types of journals, which have argued for the existence of tipping points in monsoons, or a little more precisely of a threshold response in the strength of the seasonal mean monsoon as it's subjected to a thermal forcing, such as a change in atmospheric aerosols, greenhouse gases, et cetera. So there's a number of papers that have argued for this sort of abrupt threshold response in the seasonal mean monsoon strength as you crank up a thermal forcing. And this has even been mentioned in the IPCC report as a possibility. And the mechanism, this is from one of those PNAS papers, is that you have this land-ocean temperature contrast which drives a circulation, and then that circulation advects moist air in from the ocean to land, which then gives you precipitation. And the idea, when you look at it in this sort of a plot where you plot the net column heating due to precipitation in the blue line right here, or cooling by advecting cooler air from the ocean over the land surface is a negative. When you add these two together, the idea is that this moisture advection feedback, as they call it here, will give you more heating of the atmospheric column than cooling in this range of W, which is their landward wind. So strength of the monsoon circulation or land-ocean temperature contrast is on the horizontal axis. Net column heating is on the vertical axis. Now, this is all based on a very simple, essentially one-dimensional model for thermally direct flow. And I've written down here the conservation equations for momentum in this model, for temperature, moisture, and then some closure for convection. You don't need to be concerned about the details here. My point is just to say that these models that have been in these various PNAS papers have essentially all omitted these very important terms, which incorporate the fact that the atmosphere, the troposphere, is statically stable and has a vertical moisture gradient. So they've essentially assumed a statically neutral troposphere and omitted some of these terms. And when we incorporate those, when we add those terms back in, we see that this dashed line, which was what their moisture advection feedback is, it doesn't really hold up at all, that when you have a monsoon circulation that increases in strength, what it does, as I mentioned before, is it exports energy from the column. You get a net cooling when you add precipitation to the vertical adiabatic cooling and horizontal temperature advection. This red line, which is the sum of all of those, is negative for every value of the landward monsoon wind. Now I'm out of time, so I'm going to skip this slide, which just shows that a bifurcation that they get in this model disappears, because I want to use my last, if I can go over by maybe 1 to 2 minutes. I wanted to just mention what we've done is that these sort of idealized models maybe are, to some people, not as convincing as looking what happens when you do a similar exercise in a global climate model. So we've taken a NCAR's global climate model and subjected it to a very wide range of different types of forcings. We've changed atmospheric carbon dioxide concentrations over a wide range from 1/4 to 16 times modern levels. We've changed aerosol emissions by a wide range. We've varied land surface albedo over India from 0 to 1. And I'm showing you the last 30 years of 50-year-long integrations for each of these forcings, all encompassed in 2 plots where I've plotted precipitation as a strength of either aerosol emissions or CO2 forcing or land surface albedo, shown in the black line. And then I'm showing you the monsoon circulation strength. And the point here is that you get these different responses. If you turn up your land surface albedo, the monsoon decreases in strength. If you turn up your carbon dioxide, the circulation decreases, but the precipitation increases. Atmospheric aerosols actually have a comparatively minor effect on monsoon strength. But the key point here is that you see no abrupt step function-like response. All of these responses might be strong. For many forcings, they're roughly linear. Where they're not linear, we have decent theory in terms of a Clausius-Clapeyron scaling for the moisture budget that would explain this sort of exponential increase in precipitation as a function of CO2. And we don't really see any kind of abrupt threshold response that you would get if you thought of this land-ocean temperature contrast as driving the flow. So I'm going to end there, being 2 minutes over. And just note that I've introduced these 2 alternate ways of thinking about monsoons. Instead of just thinking of land-ocean temperature contrast driving the flow, I encourage you to think of them either in terms of an energy budget, where you're supplying a certain amount of energy to the column, eventually by radiation heating the land surface then heating the atmosphere, and then the energy budget, the atmospheric energy transports having to be consistent with that, or think of it in terms of land surface sensible and latent heat fluxes together with radiation setting the surface air moist static energy, that being communicated to the troposphere by moist convection, and the circulation being consistent with the horizontal temperature gradients that you get. And when you think of those 2 frameworks, you can encapsulate, you can understand much better the observed interannual variability of monsoons. You can think about how monsoons respond to high latitude thermal forcings, and you don't get into these sort of erroneous situations where you might think of these spurious feedbacks that result when you omit terms in the energy budget. So I'll end there and take questions.